Okay, so they want us to talk a little bit about the Rayleigh criterion. So let's suppose you've got a couple pits like this, right? We want to be able to resolve those pits, right? Those pits are a distance, they're separated by a distance r. Okay, so I'll go center to center, call that r, right? And we might be viewing them through a little aperture here, and the aperture might be d away, right? If d is this distance here, okay? Now the first approximation is that that angle, right, the angle that this makes, see if I can draw that, right, that angle right there, okay, that angle theta is just r divided by d, right, and that the approximation there is, of course, that r needs to really be a circular and arc length, but, you know, if the angle's small, that doesn't matter, okay? And then this is the Rayleigh criteria, is that if you take 1.22 times the wavelength you're using, and then b is this aperture, okay, that's b, right? That's the diameter of the lens in meter, of the CD lens, right? In meters, then that's the relationship, is that the smallest angle you can resolve is 1.22 times the wavelength divided by the aperture. So what that means is that the bigger the aperture, the better the resolution, and the smaller the wavelength, the better the resolution. And we already know that. We know that small wavelengths have better resolution, right? And so let's see if we can solve a problem with this, right? And then this is, by the way, the wavelengths that the different readers use. Okay, Blu-ray players, of course, use a smaller wavelength than that. They use blue light, right? DVDs use that would be a red light. This would be like an infrared almost, right? So large a wavelength, right? Almost infrared. Okay, so basically the DVDs have closer spaced pits, so they have to have a smaller wavelength that they're using because of that, right? Whereas CDs, they're farther apart, so the wavelength can be larger. Okay, so so what is it? It's theta is r over d is equal to 1.22 lambda divided by b, right, is our relationship. So DVDs have pits that are 0.74 micrometers apart. If the lens has a diameter of 4.2 millimeters, the laser has a wavelength of 780 nanometers. What must be the maximum distance from the lens to the disc, right? So we're solving for the distance d, so the reader can resolve the pits, right? So let's plug in our numbers here. R is the distance apart, right? So 0.74 e to the minus sixth meters, right, divided by d, which is what we don't know, right, is equal to 1.22 times lambda, which is, let's see, 780 nanometers, right, divided by, what's our aperture? 4.2 millimeters, so 4.2. Right, I'm putting everything in meters because that's easy, right? Okay, so now we can solve this. Basically, it's d is going to be this number divided by all of that stuff, right? So 0.74 e to the minus sixth divided by, and I'm just going to put it in parentheses 1.22 times 780 e minus 9 divided by 4.2 e minus 3, because that's what a millimeter is, right? And I get 0.003266 meters, okay? Okay, which is 3.3 millimeters, right? Let's just go back to this thing here. The importance of the Rayleigh criterion, we talked about this last year, is that when light goes through a lens, it creates this interference pattern. So it becomes as the diffraction pattern, right? It becomes hard to discern whether you've got one thing or two things. So these are two objects that are separated at the Rayleigh criteria. We can unambiguously tell that there are two objects there. Closer than that, we say that it can't be resolved, and more than that, we say that it can be. And you could argue about that, but let's not. This is the notion, though. What this does is it basically places the maximum of one on the minima of the other one, right? And when that is the case, then we feel like we can resolve them, okay? So anyway, yeah, thank you for being mindful of the blue pen.